In this video, I'm going to demonstrate how you can use internal triggering and the read query to make a measurement on a pulsed signal. We're going to trigger on the rising edge of the signal shown on the screen, and we're going to measure the power in the area that I've got circled. We could use PMA12 software that ships with the sensor. However, we're going to make this measurement programmatically using the interactive I/O, which also ships with a sensor, just like you would make the measurement in an automated test system. The sensor utilizes standard Skippy commands, whether you're using the USB human interface device that you can connect to any computer with, or if you're using USB TMC, the test and measurement class, and your favorite VESA I/O libraries, or the SPI interface, and you're connecting directly to the sensor using an FPGA or microcontroller. We'll go over these commands again when we make the measurement in just a minute. Here's a drawing of the pulse we'll be measuring. Remember, this is a true RMS sensor, and it's a true RMS measurement, so it's not a high-speed pulse. When the pulse occurs, we get our trigger, and we have a 25 millisecond delay so that we're measuring at the top of the pulse in the center, and then we have 31 averages, each being 1.6 milliseconds apart, giving us about 50 milliseconds, which is the target of our measurement. Okay, the interactive I/O is up and running. I'll start by clicking the circular arrows to refresh the list of sensors, and then here's the sensor drop-down list. There's the sensor. If there were more than one sensor, they'd be listed in this list, and we could select the one that we wanted to interact with. I've selected our sensor. Now I'm going to send a star ID in just to make sure it's there and working correctly. And it is. There it is. It's a LB5900. There's a serial number, and there's the firmware revision. Now I want to make sure that the sensor is at a known condition when I start this demonstration, so I won't get any odd results. So I'll send the sensor a preset default, and that'll put it in a known condition. Now I'm going to change for this demonstration the measurement rate. Now the measurement rate is how quickly readings are collected and sent to the averaging system, and we have MRAT Super. It's a Ladybug exclusive command. It's not in competitive sensors, and the rate is 1.6 milliseconds. Now I'm going to set my averages to 31. So the measurement is going to consist of 31 averages, each of them being 1.6 milliseconds in length. So that'll get us pretty close to the 50 millisecond measurement that we want to achieve. So now I have to address the triggering system, because right now the sensor is running essentially free run. So we're going to set init continuous to off so that we can tell it when we want to make when we want to trigger our measurement. The sensor also has a built-in trigger delay, so when you initiate a trigger, the sensor has a short delay that it inserts, so that the rise time of the front end of the sensor is taken into account. We're going to do that manually, so I want to turn trigger delay automatic to off. And now we also are going to internally trigger this measurement, so it's going to trigger on the rise of the pulse that we detect inside the sensor. So trigger source will need to be set to internal. Now these are on this drop-down list because I've already done this in preparation for this video. Now that we've set the trigger source to internal, we have a rather unique pulse with its base level being fairly high. So we're going to have to tell the triggering system what level we'd like it to trigger at. So we'll do that using trigger level. We'll set that to -5, which should be adequate. Remember that not only does it have to locate the rising edge of the trigger, because we're triggering on the leading the positive slope, it also has to rearm, which means it has to pass the hysteresis. We're using the default hysteresis for this measurement, but it will have to fall below 5 to something like -3 or rather -7 or so to rearm the triggering system. Now we're ready to make the measurement, except that we haven't set our trigger delay, so we'll do that now. Trigger delay, we'll set it to 25 milliseconds. So it'll when the trigger occurs, it's going to wait 25 milliseconds before it makes our 31 average long measurement. So it's going to take a total of about 75 milliseconds. The measurement's going to be 50 of that. The delay will be 25. And now we're ready to make that read, the triggered read measurement. And here we go. So the green bar is the time after the read was issued until the pulse occurred. And remember, as soon as we issued that read, the system started collecting readings. They were unaveraged at that point, so there's a loaded buffer full of readings before the trigger occurred. We could actually access those if we wanted to. In this case, we've read minus 0.175 dBm, which is quite close to our expected 0 dBm reading. Now, just to make sure, just to take a look at our off-state pulse power, I'm going to put a long trigger delay in here. I'm going to set to 1/4 of a second, 250 milliseconds. So since our pulse is a little over 100 milliseconds long, we'll be well clear of the pulse. It'll trigger, it'll wait, the pulse will go by, and then it'll start measuring, and we should be able to read the off-state power using this long trigger delay. And there it is. Our off-state power is minus 12 dBm, 12.48, which I think we targeted 12. We're supposed to be minus 12.5. So that's exactly what we'd expect. And so that's. Thank you for watching our true RMS triggering demonstration.